All right, so now it's time to talk about the Go garbage collector. Now, I could sit here and tell you that Go's garbage collector is a, are you ready, non-generational, non-compacting, concurrent, tricolor, mark, and sweep collector. I could give you all of those words, and honestly, it's not going to make you a better Go developer. But, you know, write them all down again anyway. Non-generational, non-compacting, concurrent, tricolor, mark, and sweep collector. You can look up just about all of that and get some real implementation details behind it. But I'm more concerned about you being a better Go developer. So what I want to focus on is really not the mechanics of the current garbage collection or collector, but the semantics of how all this stuff works. Now, as the recording of this video 1.15 is in beta, and this garbage or the semantics for the most part haven't really changed too much over time, so I do expect this material also to be very, very relevant going into 1.16, 17, and beyond. Now, one interesting thing about all those words that I gave you was the idea that the garbage collector is not a compacting garbage collector. The only reason that's interesting is because it means that the memory on the heap is not moving. So once an allocation is made on the heap, its address is fixed for the lifetime of that allocation. And the reason that's interesting is because Go knew early on that it was going to be heavily dependent on the use of C libraries for third-party things like, say, Kafka access. And if we had a collector that was moving memory around, we'd have to start implementing things like pinning memory to leverage those C libraries as another level of complexity we didn't need. So from a mechanic standpoint, I think the only thing that's interesting is that memory isn't moving around on the heap. But beyond that, I really want to focus on the semantics now. Now, if I asked you to write a garbage collector, then there are things, or at least engineering decisions, that you would have to make in order to make sure that you're writing the collector in a way that is, say, mechanically sympathetic for your needs. There's lots of decisions to make, right? Like, what is your priority of the collector? It could be performance. You might want to write a collector that can start and finish the collection as quickly as possible as a way of maybe minimizing the impact that you have on the application. That's one option. Another option could be that you care more about application throughput while the garbage collection is running. So maybe it's more about really balancing the time that you're spending from a GC perspective, and the application is spending. Maybe you care about resource usage, and so what you're really trying to do is balance out the amount of, let's say, memory resource that's happening in any. I mean, there's all of these little things that you'll have to make decisions on, right? And then you have to choose a mechanic for the different collectors. So what I want to do is kind of focus on what Go takes as a priority for its collector, because that will help you later on with tuning your apps around the pacing algorithm in the garbage collector. So from my perspective, Go's garbage collector takes two priorities. One, tries to make sure that the application has the highest level amount of throughput during collection. We'll talk about how that works. And the garbage collector really cares about memory resource usage. One of the things that's great about Go is that it's a language born from cloud usage. And the Go team knows that there's a good chance your software is running in the cloud, hopefully on Google's cloud. And, you know, resource management's important, not, you know, for scalability, is for pricing, the cost, right? So ideally, Go is really trying hard to always maintain the smallest resource footprint possible to maybe keep those costs down. And we should understand that because it could affect certain applications, as you'll see in this training, performance here and there. So let's kind of focus on where those priorities come from. But really, one of the first questions you have to ask yourself, even if you're designing your own garbage collector, is when should the first garbage collection take place? That's a big question. When should the collector decide that it's time to make a collection? Now, there is one knob in Go. Go is really about convention over configuration, but when it comes to the garbage collector, there actually is a knob in Go. It's called the GC percentage. You can get that from the debug package, but there is an environmental variable called Go GC, and the default setting for this knob, the GC percentage knob, is 100. And what that 100% means is that, well, it means a lot, honestly. But as it relates to when should we start the first collection, when GOGC is set to 100, which represents 100%, then the first collection, all right, the first GC is going to start when the heap reaches 4 megs of memory in use. So when the first 4 megs of memory is in use on the heap, then the first garbage collection will take place when the setting is set to 100. All right? And we'll just use the defaults at this point. Now, what happens when we start that first garbage collection? Well, the garbage collection really runs in 3 different phases once it starts. Now, the first phase of the garbage collection, I call mark start, and this is a stop the world phase. When I say stop the world, what I mean is literally there is no application work going on at all. Phase 2 is marking, and that's really what collection is all about. It's really about marking values that are in use and identifying those that are not. Now, this is a concurrent phase, which means that garbage collection is happening at the same time your application is running. And then there's a final phase called mark termination, and this is also a stop the world phase. Again, no application work is getting done. Now, one of the things that the garbage collector wants to do is minimize latency, maximize application throughput while we're cleaning up the heap. It's a big part of the garbage collector's priorities. Now, we know that when a garbage collection takes place, there is going to be latency costs. As you remember in earlier videos, when I said to you that why is my program not running as fast as it otherwise could be, it's because there's latency slowing it down. We always have to have latency working for us, not against us. We're going to talk about where this latency is coming from, because that's going to help you understand how to be more mechanically sympathetic with the garbage collector. But we do know that if we add these 3 phases together, then we're going to get the total amount of time it took to do a garbage collection. Now, I can't tell you what this is going to be because every single application is different. Applications that are single-threaded are different than multi-threaded. Applications that are very transient with the memory that they use are different than the ones that are not. And so I can't just give you numbers here about how long that's going to take. A lot of the applications that we will look at in this series will have the applications that we're going to look at. We'll see a garbage collection take anywhere from maybe 200 microseconds to maybe a full millisecond. Okay, so we have to be really careful when I tell you how long any particular GC may or may not take. Now, with that being said, one of the things that the garbage collector does want to do is make sure that these 2 stop the world phases are fairly small and consistent for every GC. And so if we add these 2 phases together, the goal is to try to make sure that the stop the world latency on any GC is less than 100 microseconds. And the garbage collector does pretty good job at keeping those two phases at or under 100 microseconds on any sort of garbage collection that takes place. It's not perfect. There are times where it may not happen, but this is, to me, one of the first kind of latencies that I want you to understand. Every time a garbage collection runs, we're going to have potentially 100 microseconds or less of stop the world. Again, no work is getting done. How long this takes, again, is really dependent on the work that we're doing, and the type of work we're doing, and the load that it's putting on the heat. So I can't give you numbers there. I can give you some goals for what we're doing here. But here's really maybe the first sort of latency that we're going to get. And we'll talk about more. Now, in order to kind of understand this a little bit more, it will help to kind of draw out a Go program here. So as I talked about earlier, when your Go program starts up, we get an operating system thread in the Go program for every thread that can run in parallel on the machine, whether it's physical or virtual, that the Go runtime identifies. And let's just imagine right now that we are a 4-threaded Go program. So I'm going to draw 4 P's with 4 M's, and I'm going to say that we are a 4-threaded Go program. You hear me say this a lot throughout the class, that we're a 16-threaded Go program, a 4-threaded Go program, an 8-threaded Go program, because it does really matter in terms of being able to have a mental model of how this stuff works. Now, with our 4-threaded Go program, let's imagine that it is running some sort of web service here. And so that means we've got 4 Go routines running in parallel, right? 4 Go routines running in parallel. So if this is a web service, we can handle 4 requests at a time in parallel. This 4-threaded Go program is telling us what our CPU capacity is. So another number I want to put up here is that when we're using 100% of our CPU capacity, that means that we've got 4 Go routines executing work at the same time. And I like thinking about our CPU capacity in this case as saying that we're a 4-threaded Go program. So if we're handling 4 requests at any given time in parallel, that's 100% of our CPU. Now let's walk through these phases and see how things change as we go, and we can see where those latency costs are. So imagine that we've now used 4 meg of memory on the heap. 4 megs of memory on the heap is now in use. So we're now deciding to start a garbage collection. And we've got to walk through these phases. Now again, the first phase of the garbage collection is a stop the world phase, which means that we've got to stop every single Go routine from running on that M in order to complete this phase. Now the question is, how long is that going to take? It really depends on a few things, though. For the programs that we're going to be looking at, that should happen somewhere between, I don't know, maybe 10 to 30 microseconds. But again, this is really dependent on what's going on the machine, on the app, and everything. But to give you a general sense, for the apps that we're going to be looking at later, probably within 10 to 30 microseconds. Now, the thing is that the important part of this phase is that we have to stop the Go routines so we can turn on a little flag that we call the write barrier. And the write barrier flag is really important because what it's going to do is allow, if an application Go routine and a garbage collector Go routine get too close to each other in memory based on different sort of boundaries that exist on the heap, that we can make sure that they're not causing any sort of inconsistencies, right? Integrity issues in the data. So if application Go routines and garbage collection Go routines are far apart, no big deal. But if they get really, really close together within the scope of the boundaries, memory boundaries that are set by the Go runtime, then we want to make sure that they get in line and they're not causing, right? We don't want data races, right? Data races where we've got two or more go routines where one's doing a write and the other one is trying to access that same shared memory location. We don't want data races here. We want to make sure everything is nice and clean.